Let's begin. We're going to be looking at a problem from section 6.1 in Projectile Motion. Problem number 54 on page 171. I encourage you before watching this video to attempt to solve the problem yourself. What we're trying to do is to draw a position versus time graph in the x dimension and a position versus time graph for the y dimension of a projectile that's hit at two different angles. This projectile is a baseball hitting a baseball bat. So maybe you've seen a baseball game before. The pitcher throws the baseball towards the batter swings the bat, and the baseball heads off in some direction if he hits it. If it's a home run, then maybe it's something closer to this vector right here, this velocity vector here. Or maybe even if it's hit really hard, it might be this velocity vector here. These are the two vectors that we'll be analyzing, and then from these velocity vectors, from these two that we'll analyze individually, there's two parts to this problem, we'll be able to draw the position time graph in the x dimension and the position time graph in the y dimension. All right, we are given the speed of the ball when it leaves the bat. That is 25 meters per second. I represented that speed by the magnitude of the velocity. That's what speed is, the magnitude of the velocity of the baseball whenever it leaves the bat. That is 25 meters per second for both of these velocity vectors. Remember, these aren't occurring at the same moment in time. Maybe you could think that the first time the batter went up, he hit it with a velocity of 25 meters per second in a direction 30 degrees north of east. If this is east towards the north, so 30 degrees. And then maybe on the second time he was at the plate, he hit the ball same velocity, or same speed, but a different velocity because it's at a different direction of 60 degrees north of east this time. We're going to look at each of these individually and build position time graphs in both the x and y dimension based upon those velocity vectors. All right, first for our vector that is oriented 30 degrees above the horizontal with a velocity of 25 meters per second, or a speed of 25 meters per second. I redrew it here but removed the 60 degree vector so that we can analyze them one at a time. I also drew the components or the projections of that velocity into each of these dimensions. Here's my x dimension component vector for this velocity, and then here's my y component vector. The ball went a little bit to the right and moves a little bit up as it travels through space. A little bit over is my velocity in x, a little bit up is my velocity in y. To find how much in y and how much in x the object is moving, well, I need at least as an initial velocity, right, because this is the moment that the ball leaves the bat, I'll use trigonometry to relate my known speed here, so the length of this vector, the magnitude of this vector, to whatever side I'm trying to find through the angle. If I'm trying to find the velocity in the x dimension, for example, that would be a side or a vector that is adjacent to my angle, and I can use the adjacent side and relate that to the hypotenuse that I know as well, which would be the cosine. So if I write the cosine of my angle, 30 degrees, that's my adjacent side, which in this vector triangle is my velocity, magnitude of my velocity in the x dimension, divided by my total velocity or my resultant velocity, which in my geometry here is my hypotenuse. Solving this equation for my velocity in the x dimension, the magnitude of that, I find that I take my resultant velocity, my 25 meters per second, multiplied by the cosine of 30 degrees, and that is my velocity of the baseball in the x dimension. That's how fast the object moves in the x dimension alone. We could take a moment to find what that velocity in the x dimension would be, and it is 21.7. I'll have three significant figures for us here, at least as an intermediary measurement here. 21.7 really would round to 22 meters per second. That's how fast along the ground the ball is moving, right, in the x dimension. Now, does that velocity change as the ball is in the air? While the ball is in the air, does its velocity in the x dimension change? No, because if we looked at the sum of the forces that are acting on the ball in the x dimension, there are no forces acting on the ball in the x dimension except perhaps drag. So because there are no forces, then there is no acceleration, right? Because the net force in the x dimension is 0, this implies that the acceleration in the x dimension is 0. So this velocity remains constant in the x dimension. Let's take a moment to look at the y dimension now. Whereas we used cosine for the adjacent side, which is our velocity in the x dimension, now we'll find our velocity, our ascent velocity, at least the initial ascent velocity, that is, the rate at which the baseball, when it leaves the bat, how fast it's going upwards, directly upwards. That would be our component here. We'll use sine this time to find the side that's opposite of our 30 degrees. It equals the y component of our velocity divided by the magnitude of our speed, or the resultant velocity. That's our hypotenuse here. Similar mathematics from before, we find that it's the magnitude of the velocity, but this time times the sine of our angle. That is what our ascent velocity is. If we want a sense of what that ascent velocity is, we just take 25 meters per second, which is our speed of the baseball when it leaves the bat, times the sine of 30 degrees, and we get it as 12.5 meters per second, or 13 meters per second, for two significant figures. That is the rate at which the ball is ascending, right? So after once, well, this is the initial velocity of the ball, right? So this is the moment it leaves the bat. Now, what did we say about the x dimension? We said, well, the moment it leaves the bat, this is how fast it's moving along the ground in the x dimension. There are no forces acting in the x dimension. We're neglecting a very important force of drag. Technically, drag would be acting on the ball as it's moving through space in the x dimension. However, drag is a very complicated force to integrate here, so we'll neglect drag. Therefore, we'll presume that there is no net force in the x dimension. Therefore, there is no acceleration. Therefore, this velocity remains the same, right? If there's no acceleration, then there's no change in velocity. Right? We can also conclude that. That's not true in the y dimension. So this quantity here represents our initial velocity in y. I'm going to add that to our known and unknown t-chart here of my velocity initial in the y dimension. This is a t-chart for the y dimension of positive 12.5 meters per second. 12.5 meters per second. All right? That's my initial velocity. Is there anything else I know about the motion in the y dimension? There is, because if I look at the forces that are acting on the ball in the y dimension, there is a force, and that is the force of gravity on the object. There's the weight of the object. Okay? We could as well say drag in the y dimension, but again, we're neglecting drag. This is equal to mass times the acceleration. This is not equal to 0, right, because there is a force acting in the y dimension. So we get that the weight, which is in the negative direction, so negative weight equals mass times the magnitude of the acceleration. We know that weight is mass times gravity. We see that mass is common to this equation on both sides. So we see that the acceleration of the object is minus g, which is 9.8 newtons per kilogram, which is the same thing as meters per second squared. Right? So negative 9.80 meters per second squared. That's something else that we know, because if we look at the forces that are acting on the baseball as it moves through the y dimension, that is the force that's affecting its motion in the y dimension. All right. So we know that as well. Now, if we're trying to make a position time graph in the y dimension, which is our more complicated dimension here, it's more complicated because we have forces acting in that dimension. Because we have forces, we have some acceleration. Because we have some acceleration, our velocity is changing. Right? So because our velocity is changing, then our position time graph in the y dimension will look a little more complicated than our position time graph in the x dimension. There's something else in the y dimension that we know if we split the motion of this ball in half. Remember, if we're looking at the ball, we draw a picture of the baseball, what is happening to it. It's going up like this, and then it's coming back down. If we split this motion right in half, it's symmetric, right? If we split the motion of this ball right in half, we know that the time on the left is equal to the time on the right, but we also know that at this maximum point, the final velocity, or the velocity at that point, is 0 meters per second, because it has a positive velocity as it goes up, and then suddenly it becomes negative because it's reached its highest height. So if the motion here is describing the first half of the ball, which it can be, then we could say we also know the final velocity in y, which is 0 meters per second. An important unknown for us to solve for here would be the maximum height, which in our case would be the change in position that it goes in the y dimension. That would be this total distance here. There is our change in y, right? From start to finish, from going at some initial velocity in y to some final velocity in y. Why did the velocity change? The velocity changed because of the acceleration. Why did it accelerate? It accelerated because there's a force acting in the y dimension. What is that force? That force is gravity. Gravity is acting because the object has some mass. All right. What is our kinematics equation that we can use to relate initial velocity, acceleration, final velocity, and displacement? In this case, displacement in the y dimension. That equation for us would be the final velocity in the y dimension squared equals the initial velocity in the y dimension squared plus 2 times the acceleration in the y dimension times the change in position of our object in the y dimension. Let's rearrange this equation for change in y. That's our unknown, so that's what we'll solve this equation for. We'll move initial velocity in the y dimension squared to the other side, and then we'll divide by 2 times the acceleration in the y dimension. That should give us the change in position that the object went through. Final velocity squared is 0 squared, so we have 0 minus the initial velocity squared. Our initial velocity is 12.5 meters per second. Square that value, and then divide that by 2 times our negative 9.80, our acceleration in the y dimension. And we find that the ball went 7.97 meters. Again, I'll keep 2 significant figures here. Actually, we'll hold on to 3, and that's why I held 3 up there. We'll assume this is 25.0. That's a more reasonable. We'll assume this value is 25.0, just to give us a bit more precision. So we'll say the change in position in the y dimension is 7.97 meters, positive. Okay. In other words, the ball, in reaching its maximum height, it went up from 0 to 7.97 meters. So that's its maximum height of 7.97 meters. All right. That's important for us because that will be one of the points on our graph that we'll need, right? We'll see in the y dimension, in the y position time graph, or the position time graph for the y dimension, that this maximum height will be very important. That is a maximum position. Question is, at what point in time did it reach that maximum height? Well, that's another unknown that we have here. Okay, change in time, the amount of time that it took for it to go up to that position. Use another kinematics equation here. We need to relate initial velocity, acceleration, final velocity, and time. We can do that with the first kinematics equation. Here's our first kinematics equation applied to the y dimension. We need to solve this equation for change in time. That's our unknown variable that we're going to relate these 3 kinematics variables to. This is our rearranged kinematics equation. Final velocity is 0. Our initial velocity is 12.5, positive 12.5, divided by our acceleration of negative 9.8. So we get 1.28 seconds. It takes our object 1.28 seconds to reach that maximum height, which means it takes 1.28 seconds times 2 to reach back to the ground, or from where it was originally launched. So this represents time up, right, up to the maximum height. It takes double that, or 2.56 seconds to finally get back to the ground. All right, so we have our critical points that we can use in order to draw the position time graph in the y dimension here. So let's take a look at that. All right. We need to draw a x and a y axis. Okay. I'll make this rather large for us. Okay. There's my x-axis, which that axis represents time, right? So I'll actually label that down here as time measured in seconds. And then I'll put my vertical axis, and this will represent my position in y. Okay. I'll label that as position in meters. Remember, this is our position time graph in the y dimension. Position time graph in the y dimension. What are our critical points? I'd like to discuss those for a moment. Critical points of position and time. We have 3 critical points that we'll label and use to draw this graph. Our first is the initial position at time 0 for our baseball, and that is that the baseball will set that as the origin, right? So it's going to be moving from the origin. Our second critical point is its maximum height. So this is at 1.28 seconds. The ball has reached a height of, what did we say the height was? 7.97 meters. Okay. This is max height, or time to max height. So here's our time to max height. Here's the max height. All right. And then our third point is whenever it reaches back to the ground. So it's back to the ground. Not there. Back to the ground after twice this amount of time. So 2.56 seconds, and it's back to 0. Those are the 2 points. This is back to the ground, where it lands back on the ground. This is when it's first hit. All right, those are the 3 points that we'll label. So our first point here we'll label on the origin. There's our first point. First point that we'll label. We'll have each of these, let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this will be 1 second, 2 seconds, and 3 seconds. So each of these will be 2/10 of a second. Our position, we're going up to 8 meters. I see 1, 2, 3, 4, 5, 6, 7, 8. All right, so we'll have each of these tick marks represent, each of these grid squares will represent 1 meter. Okay, so 1 meter, 2 meter, 3 meter, 4, 5, 6, 7, 8. All right. All right, now we need to plot these points. We have our first point plotted right when the ball was hit. Second point would be at 1.28 seconds. That's at about midway here, so that's going to be about at this point. And at that point in time, what is the position of the ball in the y dimension? The ball is 7.97 meters up in the air. Right, it's right there. That's going to be our second point. Right, that's its maximum height. And then where's the ball? When does it get back to the ground? That's our third critical point at 2.56 seconds, 2.2, 2.4, 2.6, just before 2.6. And we don't need to go up at all. That's when it's back on the ground. And so these are our 3 critical points. Now we just connect those with a smooth curving line that represents a parabola. This is maybe the hardest part, at least for freehand. Right, there's our inverted parabola. Those are the 3 critical points. This is our position time graph for our 30-degree hit. Our position time graph in the x dimension is very simple because we do not have acceleration, we find that the position of the ball, if this is time and this is position and this is the position time graph, we see that once the ball is hit, it travels with a graph like this. We know that at this point in time, I'll draw a general graph. At this point in time, if this is 2.56 seconds, then the ball actually stops, right? Stops moving position, so the rest of this part of the graph is gone, right? Its position at that point in time we can find, right? That would be that if the ball traveled in the air for 2.56 seconds, and that whole time it was traveling in the air, it was moving at a velocity in the x dimension at 21.7 meters per second. And that tells us that the ball traveled 55.6 meters to the right. So this position would be 55.6 meters, because the whole time the ball was in the air, it was also moving in the x dimension. Here was the magnitude of velocity in the x dimension. So this should be 55.6 meters. The slope of this line, which we know the slope of a position time graph is the velocity of the object, the slope should be 21.7 meters for every 1 second. The same procedure would be followed for our second ball that was hit at 60 degrees. The difference there would be more of the velocity, that velocity that was 25 meters per second, would now be in the vertical dimension rather than the horizontal. The ball would likely go higher and be in the air longer, but would not be traveling at the same horizontal velocity or velocity in the x dimension.